I've been talking about doing the Laplace transform to solve differential equations. However, so far, all of the examples that I've done, I could have used the method of undetermined coefficients, which I had talked about previously in a different video. So in this video, I want to start to consider discontinuous functions, the idea being that these would not be able to be solved using older methods. We would need the Laplace transform. And to do this, I'm going to start by defining two special functions. I'm going to start with the unit step function. So the unit step function is denoted by u of t. The unit step function is 0 when t is less than 0, and 1 when t is greater than 0. So if we draw a quick graph here I have my axes, and here will be the point 1. If t is less than 0, my value is 0, so I will just be on the axis. And if t is greater than or equal to 0, I'm going to be equal to 1. So I'm going to step up to 1. And if t is equal to 0 or bigger than 0, I'm going to step up and be at the point 1. So this is my unit step function. We can modify this function slightly into u of t minus a. In this case, it would be equal to 0 when t is less than a, and 1 when t is greater than or equal to a. So if I go back and think about what this looks like and what this means, here I have my graph. Here's y equal to 1, and we'll let this point right here be equal to a. In this case, if t is less than a, I'm just going to be on the axis. And greater than or equal to a, I'll jump up at the point 1. So this is a way for me to shift over where my discontinuity is. The next way I want to modify this is doing a times u t minus a. This will still be equal to 0 whenever t is less than my little a, but it's going to be equal to capital A if t is greater than or equal to my little a. So if I go ahead and draw my graph again, we'll let little a be this point here, and capital A will be on my y-axis. In this case, as long as I'm less than a, I'm still going to be equal to 0, so I'm still down here on my axes. But once I hit the point a, little a, I'm going to jump up. So this allows me to change the height of this step function. The next function I want to define is the window function, which is very much related to a step function. It's going to be denoted by pi of a comma b. This is defined as the step function u evaluated t minus a minus u of t minus b. It's 0 if t is less than a. It's equal to 1 if t is between a and b. And then it's equal to 0 if b is less than or equal to t. So it allows me to both step up and then step back down. So all we need here is that a is less than b. I'm going to pick a to be here and b to be over here. As long as I'm less than a, this value is going to be 0. Between a and b, it's going to be equal to 1, so we jump up here. And then at b and after that, it will be back equal to 0. So it allows me to both step up and step down. Let's consider this function here. So it's 0 between 0 and 2. It then goes to t cosine t between 2 and 10, and then it's 0 again. So we can define this as t cosine t times the window function between 2 and 10, since that's where my discontinuity is. This would mean I am t cosine t times u of t minus 2 minus t cosine t u of t minus 10. So all I did here is substitute in what the window function is. Let's do another one. Here I have my discontinuous function and all of its discontinuities. So the first value of the function is 3, and that happens between 0 and 2. So this would be pi 0, 2. The next one is just 1, so I just have a pi, and this one will go between 2 and 5. The next function value is t, and that comes between 5 and 8, so I have pi between 5, 8. And then finally t squared over 10, and this one just goes on indefinitely, so it's just going to be u of t minus 8, since I don't have an ending point. And if we want, we could write this out. This is 3 times u of t minus 3u of t minus 2. This term here would be u of t minus 2 minus u of t minus 5. The third term, this is t times u of t minus 5 minus tu of t minus 8. And then finally, plus t squared over 10 times u of t minus 8.